I would like to welcome to the stage our illustrious panel today, starting with Josh Sears, Senior Vice President for the Drilling and Evaluation Division at HalLabs. Reggie DeRoche, well known here in Houston, President of Rice University and invaluable member of our HalLabs Labs Advisory Board. Earl Jones, operating partner with DCVC. Rajesh Swaminathan, partner with Khosla Ventures. Will Chur, director of the Precourt Institute of Energy at Stanford University. And last but by no means least, our facilitator, MC, and managing director of HalLabs Labs, Andres Cabada. Over to you, Andres.
Thank you, Senator Maynard. Thank you once again. That was a treat. That was a great way to get our day started, and it's going to be a great day. I'm really looking forward to the rest of the lineup. A little bit of context maybe for those of you that haven't been to one of these before. The way that we run these is we're going to play a 5-minute video from each of the companies. So the pitches are pre-recorded. That way we keep them honest to 5 videos, and we make sure that they're focused on the right stuff. And then the panel here, outside of myself, I'm generally going to be the timekeeper and MC. The panel will be asking questions of the companies. Each company will get 7 minutes to answer questions. Don't take it personally, guys, if I run you off stage. I'm just trying to keep everyone on the same schedule. So we have 10 awesome companies here today. But I'll just run quickly through who all's going to be on stage, and then we'll welcome the first one. So we'll have Noon Energy. Then we will have Nandina. After Nandina, we will have Deep Fission, followed by, sorry, I'm flipping through my sheets here. We'll have Found Energy. Then we will have HGenium. We'll take a break after the first 5. And we'll have CorePower Magnetics, Tidal Metals, Ebb Carbon, Aquora, and finally Carbogenesis. So it's going to be a great lineup. We're going to get started now with Noon Energy, and we'll play the clip. And then Chris Graves, the CEO of Noon, will join us here on stage.
Hi, I'm Chris Graves, co-founder and CEO of Noon Energy. We're developing a new energy storage system that provides ultra-long duration storage that is multi-day to seasonal capacity to deliver 24/7 year-round clean, reliable electricity. A quick overview of the company. We're developing the leading technology and product in this space with some very unique and superior fundamental properties. It's a highly differentiated product that is complementary to lithium-ion and other conventional batteries, really able to deliver the lowest cost clean, firm power from solar and wind sources. We've demonstrated a strong execution and scale up building multi-megawatt-hour modular containerized systems. You can see a photo over there on the right. Also put together a strong supply chain for productizing these systems and have a large customer pipeline with product developers, hyperscaler data centers, and others. You may be aware the addressable market here is very large. That $3 trillion number is from a report from 2021, and this is before the AI data center boom. So big opportunity. We're gearing up for our Series B fundraise, and over there on the right, you can see our collection of great investors and grants and funding received and the team size. We call our energy storage system a reversible electrofuels battery. It has a very low cost and very high energy density storage. This simplified diagram shows the 3 core components of the system. The power block, which hosts the core technology, which is a reversible solid oxide fuel cell technology. We're leveraging that existing supply chain for another application, a fuel cell application that is quite unique in the battery or energy storage world. The discharge tank holds the discharged storage media, and the charge tank holds the charged storage media. And these storage media are high energy density water and carbon-based industrial gases that get converted and stored. Also important to mention, the system has independent sizing of the energy capacity, the storage tanks, and the power capacity, the power block. And that's similar to pumped hydro storage or like a flow battery, but orders of magnitude higher energy density than those and very low cost incremental energy capacity. Just to give you a quick photo of our largest system we've built, this containerized demo system stores up to 10 megawatt hours of energy capacity, and this one is fully built and awaiting deployment. It was built under a project funded by the California Energy Commission. We'll soon be field testing this one. And just to give you some of the key takeaway numbers and metrics here, the 100 plus hours refers to that multi-day to seasonal storage capacity at these long durations. We're looking at below $20 per kilowatt hour capital cost. You could compare that to regular batteries where it's often 10 times higher cost. And that's thanks to this very abundant materials used, the elements in the storage media. And that leads to in the range of 1% of the critical elements compared to lithium-ion batteries. Very good for supply chain security, not depending on foreign entities of concern for the supply chain. And then at the bottom, as we mentioned, the very high energy density leads to a small footprint, which is very unique and valuable. We have a very capital-light manufacturing and business model. We've lined up the supply chain already for the core components. You can see Noon is in the middle of this value chain, and we're doing system assembly from a lot of these off-the-shelf components, and then working with project developers to deploy for these use cases. The current revenue model focuses on hardware sales of the storage system, additional revenue from long-term O&M agreements for the customers. We're also considering as a service and other non-standard models as we talk with certain customers. So this path to scale the manufacturing that you can see here is a key reason we would like to partner with HalLabs. We can only get to market through scale-up manufacturing expertise and real-world deployment, and Halliburton Labs offers this industrial energy systems know-how and infrastructure to help this multi-day storage type of technology that we're developing scale fast and meet the moment. Noon is targeting several market segments that range from smaller deployments in the hundreds of kilowatts to larger scale multi-megawatt, even gigawatt scale projects. In the near term, we're targeting high-value market segments like behind-the-meter, commercial, industrial, remote, or island microgrids. And in parallel, we're signing milestone-based offtake agreements with large industrial loads who need prime power and flexibility and are willing to partner with us on the smaller scale projects at first to help de-risk. We have a strong commercial pipeline, as mentioned earlier, for both near-term pilot projects and longer-term, larger offtake agreements. And a quick snapshot of the team. It's a unique one, a cross-disciplinary early-stage team with deep engineering expertise, marketing, analytics, strategy, and commercialization expertise as well. And briefly, how we'll leverage Halliburton. So we built the prototypes, proven a demo, secured a strong commercial pipeline. Now we're ready to scale. And Halliburton Labs can unlock our growth by connecting us to partners, customers, and insights while helping us scale cost effectively with operational expertise and supply chain. And the timing is urgent. The AI revolution is driving huge electricity demand. With Halliburton Industrial Muscle, we can make it happen together. Thanks.
So first question, sorry, I scrolled by it here. All right, first question. So what is the single biggest technical or commercial risk that could delay adoption, and how are you mitigating it?
Great question. Also, good morning, everyone. So thanks for having me here. Interesting to watch my own video, so that's great. Yeah, so biggest technical or commercial risk, we've actually gotten through quite a lot of those. You can see sort of years of building the company here. On the commercial side, that pipeline that was very briefly shown has definitely de-risked some of the demand there. So, we're lining up these offtake term sheet agreements and other things like that. So I think that's pretty strong. On the technical side, science totally behind us, even engineering of these larger systems. Obviously, there's sort of a step from there still to make it, designed for manufacturing, full product launch on a, coming out of a production line. So that's our next step. One of the reasons we're, of course, interested in working with Halliburton Labs and others, we're looking at that, scale up and even, contract manufacturers, things like that. But really getting into the sort of logistics of scale up, I would say. Yeah.
Hello. Thanks, Chris. Could you tell us at what point you become cost competitive with the current technologies that you're using?
Yeah, great. Cost competitive with regular batteries, is that kind of the, yeah. Actually, funny enough, that demo system, if you take just the energy capacity, it's already cost competitive with like, regular lithium-ion batteries, just because we have that very low cost of incremental energy capacity. That's not good enough for that, sort of 6 cents a kilowatt hour levelized cost thing, but it is like competitive on an energy capacity basis. But yeah, we have obviously some steps to, manufacturing volume and things to get the cost down to, fully hit these targets we've talked about.
Well, it's a pleasure to be here, and I really want to just start by thanking Halliburton Labs for the opportunity to be here. What you're doing at HalLabs is really quite special. And I wanted to also say to all the companies presenting and all the entrepreneurs who are here, thank you for choosing to work and dedicate your life on things that are important. My question for you is, can you talk about safety and maintenance? Big issues with respect to energy storage.
For sure, yeah. Broad topic, so I'll do my best. Yeah. Safety-wise, usually we would be compared to lithium-ion and other regular batteries. So in that sense, no thermal runaway type flammability issues. The electrolyte is not flammable, so much safer in that regard. You still don't want to put it indoors as an outdoor battery. There is CO2 gas in the system, right? Non-toxic, but you don't want to it will displace oxygen and that kind of thing. So overall, high safety though. What was the other part? Maintenance, yeah. So the main operation and maintenance of this type of system, we have sort of a known lifetime of one of the components there, the electrochemical cell stacks. And like it was mentioned in the pitch there, based on a salt oxide fuel cell technology, already kind of known what the lifetime of those stacks are. And so we've assumed sort of a conservative number there, and the main O&M cost is the periodic replacement of those stacks factored into our cost models.
So Chris, you talked about a 100-hour battery. That's an interesting market. What would you do differently if you have to meet a 10-hour, 20-hour duration battery and be cost effective? What would the reliability or the discharge rate look like?
Yeah. So we can certainly do 10 or 20 hours capacity. As you guys might have seen, the independent sizing of the energy capacity and power capacity means that you just have less tank capacity to do that. I don't think we included that sort of cost graph. You guys can take a look at the website. It has this. We're competitive with lithium-ion at that duration. That's not a good business case to be just competitive. A lot of companies are aiming for that 10-hour market and really almost the same price as lithium-ion. So we're going for the ultra long duration, as we called it. We kind of came at the problem as, what do you need to fully balance solar and wind power? There are other applications on the grid as well. But that's where you need those numbers, and that's what we're addressing. Yeah.
Well, very, very happy to be here, and I couldn't think of a better place to bring innovation and industrialization together when it comes to energy. So, Chris, I'll piggyback off Rajesh's question here. One of the reason lithium-ion battery became so successful for grid storage is they participated in merchant markets, so being able to buy and sell on the fly. Do you see your technology being able to participate in merchant markets?
Yes. So you're kind of talking about doing some things like arbitrage or other kind of, and that's obviously had a big effect here in Texas as well. We can do that. There's several business cases we've done, like simulations, including arbitrage. There's some commercial industrial behind the meter, time of use type savings as well. So price signal driven stuff we can certainly do. And in terms of response time to be able to do that, we're able to do that as well. And then one kind of unique thing, not that we're going to do it in the same way as lithium ion, but you don't have to worry about the energy capacity in our case, right? So in the other case, if you're fully charged or discharged, you can't do more of that. But in our case, you just oversize because it's so inexpensive.
Very good. We have another minute left, so I'm going to squeeze in a question. I said I wasn't going to ask any, but hey, we got some time. So given the chemistry of the battery, I'm curious about kind of the long-term reliability or any concerns that might exist around the electrodes, whether that is carbon deposition, whether that's delamination, just in general, the reliability of the system in the long run. Can you comment on that a little bit?
Yeah, sure. Yeah, it kind of ties into the operation and maintenance question. So the overall system, we're assuming the 25 or 30-year life, and things like the tanks are going to be like almost that entire life. But as was mentioned, the electrochemical cell stacks, they do have a certain lifetime. It's high temperature. There's like corrosion of the stainless steel interconnects, things like that. We've actually avoided some of the issues that you mentioned, but there are others. So it's not like it has the full 25 to 30-year lifetime. So that is the main maintenance, is to do that module replacement periodically. Yeah.
Thank you. Well, we're right on time, Chris. This has been great. Thank you so much for being here with us today.
Yeah. Thanks, everyone.
Now, next, joining us, Karina Katie, CEO of Nandina Rem, all the way from Singapore. Karina, thank you so much for being here with us today.
Hi, I'm Karina Katie, CEO and co-founder of Nandina Rem. What do advanced industries like aerospace, energy, and defense have in common? They all depend on carbon fiber, which is facing a raw material supply crunch. In 2023, global demand for carbon fiber was approximately 115,000 metric tons. By 2030, it's projected to more than double. Wind energy is on track to surpass aerospace as the largest user, with 20,000 metric tons needed for just wind blade manufacturing alone. We're already seeing supply risks delay energy projects. At the core is a materials access problem. Energy players are locked out of secured supply, forced to overpay for overspec fiber or settle for poor substitutes. At Nandina Rem, aviation was our proving ground. Energy is the next frontier, and the need for secured, high-performance supply has never been more urgent for next-gen power and industrial resilience. This is a $17 billion global market. Our near-term focus is high-performance aerospace, an $850 million segment where we've built credibility, proven performance, and secured customers. Now we're leveraging that expertise to expand into energy and defense, high-potential sectors with surging demand and massive strategic value, representing a $4 billion opportunity. But this isn't only about demand, it's about resilience. That's where Nandina comes in. Our rapid production model redefines how carbon fiber is processed and delivered. We cut lead time from 12 months to 2 and shrink innovation cycles from 5 years to just a few months. Our proprietary Savalysis process produces aviation-grade carbon fiber at 71% less energy. And that's possible because we have eliminated heat-intensive processes, cutting thermal energy consumed from over 1,000 degrees Celsius to just ambient temperatures. It means advanced high-performance materials can be deployed faster across aerospace, wind, and energy storage applications. We are the only company delivering a tech solution that meets all 5 critical performance markers in this industry, including fiber integrity, broad composite compatibility, and aviation-grade compliance, and we're uniquely positioned to meet both aviation and energy-grade specifications. This is remanufacturing, a new standard for circular carbon fiber of next-generation strategic applications. Carbon fiber supply chains are shifting fast. A leading OEM has already chosen to partner with China on composites recycling. Every nation must build resilience by onshoring production and eliminating dependence on China for critical infrastructure and supply chains. We witness this even more acutely in the United States, with both the Department of Defense and the Government Accountability Office flagging foreign dependence on such supply chains as a strategic vulnerability, one with no easy substitutes. But this is a challenge faced worldwide, and the next 18 months will define who sets the global standard. It's not just a market opportunity, it's a national security imperative. Nandina is ready. We have a proven production model, existing customers with some of the world's largest companies, scaling in months, not years, backed by regulatory and government agencies. We've demonstrated strong traction, landing partnerships with Qantas and Emirates, and as recently announced in their investor report, Southwest Airlines. In just 2 years, we've also progressed from early contracts to 3 expanding revenue streams: co-innovation, material sales, and asset services, each scaling in parallel. Our current primary revenue driver, co-innovation sprints, enables customers to unlock new markets and products with Nandina's materials. Directly collaborating with our customers on product development has been key to helping us gain deep, real-time understanding of their specific technical challenges and market requirements. As we scale, it's our team that makes it possible. We bring deep expertise across material science, energy, product technology, and sustainability. We're raising $12.2 million to scale certified production and accelerate our global commercialization over the next 12 months. This capital is being deployed into feedstock preparation, modular plant design, and systems integration, areas where Halliburton excels. With Halliburton Labs, we gain the ability to accelerate beyond aerospace into energy and defense through leveraging their expertise in policy, next-gen energy applications, and global customer connections. Industries are at a breaking point, but the opportunity is now. Nandina is ready today with proven technology, real customers, and secured feedstock.
Thanks for being here. You traveled a long way, and you look
It's worth it. It's
you look
fine.
very alert. First question from me is, as a structural engineer, I'm always interested in how materials that are recycled perform versus those that are virgin. Can you talk a little bit about the performance, the reliability, and the cost?
Yeah, absolutely. So a lot of our feedstock comes straight from structures. I always love to show and tell because we make products that customers love to buy. So this is a floorboard from an aircraft. Every single one of you that have walked on an aircraft, this is what your seat is attached to, and this is what's in between the seat and your cargo hold, basically. It's an incredibly strong material. It's an aramide honeycomb board that has a carbon fiber face sheet on top. So a key thing that we focus on is how do we keep that integrity of the carbon fiber that goes into a structure, but it doesn't go back straight into this structure. So we work with airlines directly to be able to put it into sort of lower hanging fruit, but in cabin parts, basically. So it's still going back on the aircraft. It still has that level of structural integrity, but it's a much more straightforward certification pathway. Yeah. Great feedstock to be able to make pretty solid end products.
Thank you. It was a great job there. Really, two questions for you, if I may. You said you've designed out high temperature processes. Could you double click on exactly what you're doing technically? And then sort of the follow-up piece to that is, with variable feedstock, how do you produce repeatable quality output?
Yeah, great question. And it's been a key part of the challenge that we work on with the Singapore National Science Agency to be able to keep that consistency and quality, right? So essentially it's a Savolysis process. We use, as ambient temperatures, benign chemicals. Certainly being in a humid climate also helps to accelerate some of that process. But so we control the feedstock, firstly, like in the selection of it itself, and then how we prepare it for each specific batch process. We're still early stage, we're only 2 years old, even though we are post-revenue, which is obviously a fantastic position to be in. What the customer needs at that end product defines that entire process. So we really have to know already what is that end customer application in order to adjust what has to happen in each batch. And that's been a key portion of how we can really just manage the consistency in the feedstock. Yeah.
Nice job. Carbon fibers, you're working with aerospace. This industry is notoriously known for really low, really long qualification, design cycle, and all that stuff. So how do you expect to generate revenues in the 2030, 2035 timeline? And given your 70% of your revenues seem to be kind of innovation,
co-innovation sprints.
How do you make money?
Yeah, so right now, the co-innovation sprints are the main source of our revenue. We do expect that to be shifting to majority material sales within the next 2 to 3 years. So I have here with me one of my materials, which is the favorite reminder for me of why the co-innovation sprints have been so effective. And also when you're dealing with aerospace materials, at the end of the day, one of the coolest things that we've been able to work on this, every single material that is in an aircraft is some of the best of that material that has ever been made. And that's even in a seat cover. So this material is actually made from blending wool fibers recycled from the seat that you sit on with our carbon fiber. It is a naturally protective material, for 750 degrees Celsius. And the reason that I'm going into this detail is we did not think at the start that there would be an on-ramp to be able to enter back into aerospace so quickly. But we got there because we went and reached out to over 200 manufacturers to really just understand how they learned with carbon fiber. And they basically helped us map out that pathway together. Both the FAA and EASA, which is the Europe equivalent of the FAA, have been right there with us from the start. They like what we are doing, really for the traceability angle, for being able to ensure origin of source. So when the regulator is able to help us figure out with the manufacturers that are actually making the parts rather than the OEMs that are just assembling, that became a huge part of our moat to figure out how to get everything to market faster.
Well, Rajesh took my question. So rather than asking another question, I will just double click on the question if that's okay. So maybe I can just ask explicitly, what is the qualification certification time now for one of these products? And how does it match up to your fundraising and operation plans?
Yeah, so it really depends on the product. One of the reasons that we don't start straight away with structures, for quite rightly, there is a very, very long, complex certification process for that. We started early on, actually not with carbon fiber. We started to just map out, so choosing a hero part. So this is an example of a part that we have with one of our airline partners. This is a part, it's a problem part. It's actually just a galley latch. And there's a huge delay of cabin materials at the moment due to 40% of the supply chain going bankrupt coming out of COVID. And so this galley latch started its life as a fuselage of a Boeing 767. And using a same type of material, so it's a direct drop-in replacement, we were able to figure out, so what has to be true and what has to be shown to be able to get this latch back into a plane. It's only been 1 year. The certification pathway is there. Obviously can't say that announcement yet, but definitely come to Singapore Air Show and it'll be a really exciting launch. We then, to be able to just understand how you would do a direct drop-in replacement, then of course this is just purely a prototype for testing sake, if you could do 100% carbon fiber replacement for this latch. And so the weight saving changed the conversation with airlines. You can feel the difference between the two.
So I guess I'm going to triple click on that.
That's fine.
Along this same line of thoughts that you're talking about, what regulatory barriers exist before your recovered materials can be used in critical, safety, sensitive structural components?
Yeah, so material performance is number one, right? And especially when you're dealing with aircraft, it has to be able to withstand G-force. Everything that is on your seat is there to protect you. It has to be able to withstand incredibly high temperatures for fire. So the performance is number one. There's no amount of whatever marketing you want to put on the product. If performance is not there, you have no shot to be able to get it to market. But it's the same thing for other industries as well. So our energy industry customers who we work on getting the carbon fiber into their tooling and their infrastructure, performance is what matters at the end of the day, and it's why they buy our products.
Thank you, Karina. We got to leave it there, but thank you so much for sharing Nandina's story with us. Okay. Up next, we have Liz Miller, CEO of Deep Fission. Oh, excuse me. I don't know how to read my notes. No. We are going to first share a success story from one of our HalLabs Labs participants. Sorry, Liz, I didn't mean to give you a heart attack. Much like we like to hear stories from a lot of the new companies that we're engaged with, we want to share the wins from some of the companies that we've worked with on. So we're going to play a video clip here from one of our portfolio companies now.
What you're going to see today is a first-of-a-kind facility. Nowhere else in the world does this exist, where a scalable process has been developed to directly convert carbon dioxide and water into a variety of carbon molecules, all made from one molecule, formate. Historically, we've all relied on new or even old biomass as a source of carbon to make and consume many kinds of products, from plastics and fertilizers to food and feedstocks. However, this has limited us to the availability of old and new biomass. The sole focus is to convert recycled CO2 into an organic molecule. Behind me, you see the results of 5 years of effort to produce the world's largest CO2 electrolyzer. It combines carbon dioxide and water and converts it for the first time into a useful liquid carbon molecule, which we can use as the foundation for building many other types of chemicals, materials, and fuels that the world needs. On my right is an analyte skid. The analyte is a material that contains water and other chemicals that we provide to the electrolyzer cell. To my left is a catholyte skid. The catholyte contains other liquid chemicals that enable carbon dioxide to combine with hydrogen to make formate. And that occurs in what's directly behind me, which is the electrolyzer carriage.
What we have here is the 4-cell stack of electrolyzers. Each cell is an industrial-size electrochemical reactor of 1.5 square meters. What this setup does is it tests 4 cells put together as a stack to convert carbon dioxide, which is let in on the other side of the cells, and the catholites and anolytes, which are flowing into the cell across the membrane to convert carbon dioxide to formate. That formate is converted to one of Okochem's products, formic acid, out here in an electrodialysis system. This is a membrane-based electrodialysis system which takes into account bipolar membranes and cation exchange membranes to do this conversion.
At Okochem, we're rethinking CO2 emissions, seeing it not as a problem, but as an opportunity to source and convert carbon more affordably and sustainably. Nowhere else in the world is there a multi-cell pilot plant using industrial scale sized cells that convert carbon dioxide into liquid carbon molecules. Our approach is simple yet powerful. Tackle the complex problem of carbon head on and turn it into something that benefits both our planet and the economy. Join us in creating a future where innovation drives sustainability and sustainability drives success.
So Todd Bricks, CEO, is not here with us today, but I wanted to share a couple of things about Okochem that are not on the video. The facility that you saw in the video is at their headquarters in Washington State. And just last month, they signed a commercial agreement to install one of the plants at an ADM corn processing facility in Illinois. So they're getting some commercial traction. It's a great story. We're very happy with the progress that we're seeing from the Okochem team. With that, Liz, now it is your time. So please join us here on stage. Please welcome Liz Miller, CEO of Deep Fission.
I'm Liz Muller. I am the CEO and co-founder of Deep Fission, an advanced nuclear company that is taking 80% of the cost out of nuclear power. We're doing that by putting our reactors in boreholes a mile underground. I've been working in the nuclear waste industry for the past 10 years, so we understand what it means to put something deep, deep underground. One of our customers asked us, what if accidentally, instead of putting nuclear waste in a borehole a mile underground, you put fresh fuel? Could it possibly start a nuclear reaction? Now, the answer was no, but it lent us to realize that the environment in a borehole a mile underground is exactly what you would want for a nuclear reactor. Why is that? Well, you have the containment. You are surrounded by billions of tons of rock. You don't need to build all of the expensive structures that a conventional reactor would need for containment. Second reason is pressure. In a borehole a mile underground, you have the 160 atmospheres of pressure that you, again, don't need to build for a traditional pressurized water reactor. And then the third thing is emergency core cooling. We have a column of water above us that we can leverage for emergency core cooling. And so we don't need to build all of the expensive systems that a standard pressurized water reactor would need to build. This means that we can take between 75 and 92% of the construction cost out of conventional pressurized water reactor technology. This construction cost is the single biggest reason that nuclear power is so expensive, and Deep Fission doesn't need any of that. So we're combining 3 technologies: pressurized water reactor technology, standard fuel, with deep borehole drilling. This is something that Halliburton Labs understands really, really well. We are drilling a mile deep, and we want to have about a 50-inch borehole. We're also combining it with geothermal. So once we create heat at the bottom of the borehole, we need to bring that heat to the top and use that to generate electricity. That is what geothermal does. So we're able to leverage 3 existing mature technologies in a way that has never been done before. We expect to be profitable from day one. So we are cutting the costs, which means we will be profitable, including for the first-of-a-kind implementation. If you look at conventional nuclear, it takes 6 to 10 years to build. It's going to cost you $15 billion for a 1 gigawatt reactor. And that's going to be about 18 cents per kilowatt hour. Now, the advantage is you can use an existing supply chain for fuel, LEU fuel, that is readily available today. Now, in contrast, advanced nuclear is 3 to 4 years to build, so a shortened time frame. looking at $8 to $9 billion for construction. So again, much better. Cost per kilowatt hour, still hard to say, but it's probably not going to be profitable, at least for the first of a kind. Now, the challenge is that most of these companies require HALEU fuel, which is not commercially available today. Deep fission, in contrast, we're looking at 6 months to build. So very, very fast because we don't have a lot of construction. We're looking at $2.5 to $3 billion for the first of a kind implementation of a 1 gigawatt power supply. That's 5 to 7 cents per kilowatt hour, very profitable, very economical, including for the first of a kind. And we can use existing LEU fuel that is readily available today, not just for our pilot reactor, but for commercialization at scale. We're thrilled that we're part of the Department of Energy Nuclear Reactor Test Program. This means that we are building our first reactor in 2026. So we expect to build one in 2026 as part of the pilot program. We will then expand this at the same location to 10 pilot holes, 150 megawatts electric. That will prove that not only can we build this, but we can do it and be profitable at the cost we say we can. Beyond that, we're looking at global expansion, and I think we have the opportunity to address data center needs both in the United States and around the world. So with Halliburton Labs, we think we can move even faster. You've got the engineering that we can leverage, particularly on the drilling side, O&M in terms of in placing things down boreholes, pulling them back up again. Supply chain, you've got fantastic supply chain partners, as well as the ability to do a lot of manufacturing yourselves, and then access to customers around the world. So in summary, I think that for nuclear right now, time is the currency, and deep fission is going to be able to move fastest, not just for a first pilot study, but for commercialization at scale and then around the world. Thank you.
Well, Liz, what a great idea. And I love the genesis story of how you took the waste, nuclear waste concept into nuclear power. I'm a former Navy submariner, Navy certified nuclear engineer in the background, as my background. I'm delighted to see the resurgence of nuclear power. That said, the Nuclear Regulatory Commission has never been, our fastest regulatory body, and this is really outside the scope of anything that they've been thinking about. How do we think and get comfort that the NRC is going to get their arms around regulating something that's so different?
Yeah, this is something that is really exciting because it is changing right now as we speak. So historically, like you said, the Nuclear Regulatory Commission has been very safe, which is great, but also very slow, which is not fantastic for the industry. But there is now strong motivation. Nuclear power is seen as a national security priority, and building nuclear very fast is part of that, while still maintaining the same level of safety standards. Important to note that. By participating in the Department of Energy pilot program, we are going to be authorized by the Department of Energy, not by the NRC to start. Now, it is the Department of Energy that is strongly motivated to have at least 3 reactors up and running by July 4th, 2026. So they are driven to get the approvals done. Now, we still have to go through all of the work to show that we are very safe, but I believe that they are prepared to review it quickly, which I also think can be done. We have modern tools now that can be used to review applications that maybe weren't possible 5-10 years ago.
Very elegant approach. Very elegant approach to the nuclear problem. Lots of new SMR companies have come up just in the past year. What makes it difficult for a NuScale or a TerraPower or any of these guys to take your borehole drill approach, and copycat, and so help us understand the technical differentiation on the entire stack?
We've got a lot of IP. So we have over 40 inventions that are pending right now. Our first patent has been allowed. We're only 2 years old, so I expect that those will come over time. But with my other company, Deep Isolation, we have now 87 patents that have issued. So we understand how to get new ideas patented. We're using the same patent legal team that we were using for Deep Isolation. So I feel really good about our patent protection. Now, what we might want to do at some point is take someone else's nuclear technology and put it down a borehole, because because I think we could save them a lot of cost too. But certainly to start, we're looking at pressurized water reactors because it is what is readily available. It's where we can get the fuel today on the spot market. So we feel like we want to start with what's easiest, and then we could branch out as we go.
Yeah, what a innovative concept in the nuclear renaissance. I completely agree that the construction cost should come down with your approach. But how about the trade-offs in the O&M part of it, especially with the reactor being so deep down?
Yeah, another great question. So we are expecting to not need maintenance on our reactors because we will just abandon them after 7 years. So the assumption is that we will put the reactor down to the bottom of the borehole. This is assuming we're using 9 fuel assemblies. And then we will leave it there for 7 years until the fuel is essentially used. We will seal it off. We will put another one on top. So if you look at the typical timeframes for needing maintenance on reactor vessels and other things, if it's just 7 years, you shouldn't need that. Now we could, if we ever needed to, pull it back out and inspect it and do maintenance on it, but we think it's going to be more cost effective to simply seal it at the bottom. So that will dramatically reduce the O&M cost compared to conventional nuclear, where you're constantly maintaining things above ground to make sure that nothing is degrading over time. We also believe that because we're so far underground, there is very little in the way that something that could happen underground that would impact humans or the environment. So we don't think we're going to need the same nuclear quality assurance standards that you would need if you're building a reactor above ground. There could be an economic loss if something goes wrong underground, but it's not going to have an impact on humans.
One of the issues with nuclear is not in my backyard. So what's your plan for public acceptance, not only domestically, but as you grow internationally as well?
Yeah, this has actually been, I think, the biggest surprise for me in the past couple of months. Everybody knows that nobody wants nuclear in their backyard, or so we thought. But over the past few months, we have been out talking to communities and signing LOIs. And just yesterday, we announced first projects in Texas, as well as Utah and Kansas. So these are communities where we've actually been out there talking to people. And we said, are you interested in this? Is this something, what are your questions? Can we answer all of your questions? And rather than not in my backyard, we're seeing, yes, please pick us. We want to go first. So this is exciting, and I just think it demonstrates how nuclear has changed over the past 5 years.
What steps are required following the pilot before the product is actually ready for commercialization? Can you walk us through that?
Yeah, another great question. So we expect Department of Energy authorization for the first one that is then going to have to move over to Nuclear Regulatory Commission approval for any commercial use of that first reactor. So we are trying to build our first pilot that is very, very close in design to our commercial reactor, because the closer it is, the easier it should be to transition that over. Now, what the Department of Energy has said is that anything that has already been authorized or approved by the DOE will not need to be reapproved by the Nuclear Regulatory Commission. They want to take a fresh look, of course, but we're looking really at what's different between that first one and the second one in order to build. So we're going to need, I don't know how long that's going to take. We've been asking, we've had good information. I'm not even sure the Department of Energy or the NRC knows how long it's going to take, but there is strong motivation to go fast. I'm imagining we're talking months, not years. Now, that means that if we build our first one in 2026, we could potentially start commercializing, build time again 6 months, so we can be ready up and commercial very soon afterwards.
Very good. Well, we're right on time, Liz. Thank you so much for being here with us today. Really appreciate it.
Thank you.
Okay. Up next, we have Peter Goddard, founder of Found Energy.
Hello, my name is Peter Goddard. I am the founder and CEO of Found Energy, where we are unlocking aluminum fuel for industrial clean heat. This is an important problem because today industrial clean heat is truly an unanswered need. You have companies ranging from pharmaceuticals to consumer goods, food and beverage. They all want clean heat, but there are few good options. Alternatives today are costly or simply just cannot perform to the specs that are needed. Heat pumps, for example, can't reach high temperatures. Renewable natural gas is expensive and difficult to scale. Biomass availability is limited. Technologies like e-boilers are vulnerable to grid interconnection delays. And this is a massive opportunity. We estimate that solving this problem is almost $80 billion problem for the US markets and globally over $2 trillion. At Found Energy, we are solving this problem with a novel fuel based around aluminum metal as an energy carrier. We build systems that take in any aluminum metal, react that with water and air, and produce energetic outputs like low carbon steam and hydrogen gas continuously. We can reach temperatures well over 2000 Celsius. We can do this completely behind the meter and off the grid. This is scalable, there are zero emissions, and we can actually do this at a competitive cost to the incumbent fossil fuel-based heat. We have lots of positive feedback from early adopters in this market, telling us just how important our solution is and that we're able to meet the challenges they have specifically around grid interconnections and the economics of clean heat. If you think about our technology as an electro fuel or a clean fuel, we are already a best in class. Making aluminum metal for the purpose of energy storage is a very efficient process already, more than 1.5 times that of ammonia. It's very energy dense. Aluminum is about 3 times the energy density of methanol, 4 times that of liquid natural gas. Very safe. You've never heard of an aluminum spill. We move around 70 million tons of aluminum each year with no problem. And there is an abundant source of low-grade aluminum scrap feedstock that will support our beachhead market at very, very competitive prices. The way our technology works is we enable aluminum to react with water, releasing that 8.6 megawatt hours per ton of energy as that steam and hydrogen gas. We do this very efficiently with a catalyst that is fully recoverable. This was developed during my PhD at MIT. We licensed that technology and we've developed a very robust patent portfolio around that. We've been developing over the past 3 years complementary technologies around power system engineering, byproduct valorization, turning this fluffy gray material here, which is aluminum hydroxide, into a value-added product. And down the road, we will be making our own aluminum using electricity by basically recharging this aluminum hydroxide so that we can expand past scrap markets and deliver renewable energy stored in aluminum to the entire industry. And again, this is a massive opportunity. We can produce thermal energy at a cost from about $15 to $16 per MMBTU. If you think about this in terms of carbon dioxide avoided, it's about $170 to $190 per ton, and that number will just decrease over time. To start, we are using abundant scrap aluminum. If we can tap into the low-grade scrap aluminum markets in the US, that creates about a $4 billion opportunity for us. Globally, that's $12 billion. And then again, we are working on our own fuel-grade aluminum production process that allows us to expand past that scrap market and enter the industrial heat market on the whole. We estimate that we can address about $70 billion worth of fuel. And beyond that, the same technology can be used in energy transportation more broadly, maritime shipping. The use cases are endless. Found Energy is led by industry veterans from Jet Propulsion Lab to major aluminum manufacturers and Shell. We've raised over $20 million to date from leading firms like Autodesk, Activate, Munich Re Ventures, Compass Ventures, and we have a team of 30 that are working hard to deliver this novel technology. The company was founded in 2022, where we started with batch 10 kilowatt reactors, and now we're deploying our first 100 kilowatt demonstrations. By 2027, we expect to be deploying our first megawatt units. We are very excited to be applying for this program. We believe that together with Halliburton's expertise in fuel solutions at scale and our novel technology, we can move very fast, very far to bring clean heat to the markets that need it the most. Thank you so much.
Nice to see you again, Peter.
Yes.
Help us understand a little bit about how you compare with some of the thermal batteries going after industrial heating. Rondo, Antora, Redox blocks, a few others?
Yep, I love this question. So we see ourselves as complementary to those technologies. Those technologies work extremely well where you have low-cost renewable electricity available on site, and then you can basically store that electricity as sensible heat, for example. We're working with folks that just simply cannot get a new grid interconnect. So this is truly behind the meter, where you have absolutely no additional electricity capacity, let alone green electricity capacity. So think food and beverage, pharmaceutical manufacturers that are really relying on natural gas, and in some places in the world still coal supply chains. Expanding the grid to their doorstep, literally will take another decade, they're estimating. And so that's where we can jump in and provide decarbonization solutions in a much shorter time frame.
If I can have two questions, quick ones. First question, aluminum is a very high quality ingredient, reactant. What are some of the other uses that would compete against heat as an output? And my second question is, how do you separate your catalyst from the aluminum once the process is done?
So if I'm understanding the first question correctly, it's what are the other uses for
other use cases that could compete
for aluminum metal?
That's right. That you can imagine. Are there higher value uses for aluminum?
So, okay, we can separate what we do into basically two markets. So one, we're taking very low-grade aluminum waste, for which there is virtually no way to recycle currently. So our initial 100 kilowatt demonstration partners are manufacturing centers that actually pay someone else to take their aluminum waste away. It's turnings and mill scrap from these machining centers. It's mixed alloy content. It's heavily contaminated with cutting fluids. And so they actually have to pay someone somewhere between even up to $700 a ton to take that aluminum and then figure out what to do with it. A lot of it just ends up getting landfilled, or it's treated as hazardous waste. So for us, it's actually a negative feedstock cost. There's really no other application. We want to be the home for all of that aluminum that no one knows what to do with. And as we've been growing the company and getting a little bit more publicity, there are people reaching out to us literally every week with new sources of aluminum that they don't know what to do with. So we just see ourselves as, again, a complementary technology to existing ways of recycling aluminum. We want to keep all of that aluminum here. This is just another thing you can do with that. In the long term, I guess your question is like, if we're making aluminum, why not just sell that into aerospace grade? And the reality is we are just making a grade of aluminum that is frankly not useful for any application. For our process, purity doesn't matter. And so we can make a very low quality crude aluminum, if you will, a fuel grade aluminum that you just actually wouldn't be able to sell on the open market. And so the only thing you possibly could do with that is actually make fuel and burn it. And then sorry, what was your second question?
Separation of catalyst from the aluminum hydroxide.
Yeah, so it's a simple phase separation. The catalyst is much more dense than the aluminum hydroxide. And at the temperatures we operate is actually a liquid. And so it just easily separates out based on density.
To reach meaningful scale, what do you see as your biggest bottlenecks? Is it feedstock, capital cost, logistics, permitting, regulations, or something else?
I think you hit all of the every single thing that we'll have to deal with. For us, there's an interesting point where we'll be transitioning from using low-grade waste as a feedstock into our own aluminum, and there's going to be, potentially a timing mismatch that we need to handle there. One thing that we are starting to develop to mitigate that is actually thinking about blending these feedstocks. We can actually take aluminum waste. So some of the folks that we're talking to think that we're an aluminum hydroxide company, or we're like a commodities mineral company. We can make high-grade aluminum hydroxides for fire suppressants, for example. And that allows us to do this arbitrage where we take very low-grade aluminum waste, we turn it into very high-grade aluminum hydroxide, and we're producing energy at a negative cost because we're basically just running an aluminum hydroxide manufacturing plant. That allows us to actually subsidize the inclusion and the blending of much more expensive sort of primary aluminum that we'd be developing. It's just a matter of how quickly we can start blending those two. But in the short term, it's quite easy to source this low-grade aluminum waste for 10 megawatt projects. Our first customers will get very lucky with very, very low cost.
Hey, Peter, thank you. What is the estimated cost and lead time to deliver a 100 kilowatt unit?
So for us, the first unit that we're running at our facility in Boston costs about $1 million, and that's just the first of a kind. And we project that those costs basically double every 10x capacity that it follows that normal power law that you see with industrial equipment scale up. And in terms of lead time, we can crank these out within a couple months.
So according to the presentation that we have on Found, your open loop process, the economics are heavily dominated by the sale of the aluminum hydroxide. If you're starting with very dirty feedstock, how are you creating a clean, saleable aluminum hydroxide? And then second question is, how important is it for you to get to the closed loop process, and what's your round trip efficiency in the closed loop process?
Yeah, thank you for that. So the hard part for what we've accomplished here is basically going from the aluminum metal to a high grade in terms of crystalline morphology and particle size aluminum hydroxide. And that is very easy for us to tune with the chemistry and the kinetics. And that's actually the part that folks that in this industry that make high-grade aluminum hydroxide, they spend a lot of energy grinding particles, for example, and doing these large precipitation reactions. So that's the hard part, and then everything else is more or less a solved problem in these industries in terms of removing conductive contaminants from the alloy content of the aluminum, for example, removing organic contamination. People making aluminum hydroxide that start from bauxite have to deal with much nastier stuff in those processes. And so we can actually piggyback on a lot of that technology that's already been developed there. We're already doing the hard part, which is really that value-added process. And then your second question, so in terms of round-trip efficiency, in terms of electrons in to thermal joules out, it's about a 70% efficient process.
Thank you, Peter. Very good. Really appreciate you spending the time here with us and coming and joining us at Pitch Day today. So thank you for spending time here with us on stage.
Thanks, everybody. Thanks for the great question.
Okay. Next up, we have Nate Thomas. Nate's the VP of Strategy at HGenium. Nate, please come join us on stage.
Greetings. I'm Nate Thomas, Vice President at HGenium. With origins at Caltech, we are changing the way to produce, out of water and air, the clean feedstocks we need for the clean hydrocarbons that will power our future. As we live now, this is our world. We are a petroleum-based civilization, reliant on hydrocarbons for our way of life. As a family of compounds, though, hydrocarbons are great. They are energy-dense, easy to store, easy to transport. The problem is that the carbon dioxide released from burning those taken from the ground is polluting our climate. However, development in alternative so-called e-fuels is heating up, with investment coming from both public and private enterprise to react clean CO2 and clean hydrogen together to produce energy-dense hydrocarbon fuels. But capturing CO2 out of the air uses a great deal of energy, primarily for actually moving that air or for driving chemical reactions, like calcining or drying. And electrolysis for making clean hydrogen, while well established, has struggled to be adopted on an industrial scale. Quite simply, direct air capture as a source of CO2 and electrolysis for hydrogen as independent processes are cost prohibitive. We're HGenium, and we have developed a fundamentally different approach towards direct air capture and green hydrogen production with a single integrated process driven with heat instead of electricity. The way this works is that over a series of high temperature and low temperature chemical reactions, we net convert water into hydrogen and oxygen. And in the low temperature reaction, one of the reagents strongly reacts with carbon dioxide, pulling it out of the air so desired. Overall, our process produces green hydrogen with the extra bolt-on feature of direct air capture, all the while driven with heat instead of electricity. And as heat is cheaper and easier to store overnight, HGenium's proprietary technology enables long-duration production of hydrogen, even after the wind has stopped blowing and the sun has stopped shining. Said another way, when compared against incumbents, HGenium has the only commercially viable carbon-negative hydrogen production technology to date. As I mentioned, our origins stem from Caltech, where the original technology was developed in the research group of Professor Mark Davis, a legend in the field of catalysis, and is the holder of over 50 patents. Our leadership team combines world-class technical expertise and decades of executive experience to become the global leader in carbon-negative green hydrogen technologies. The global demand for hydrogen in 2024 was approximately 100 million tons, with essentially all being produced from natural gas at the sites of use for chemicals production and oil refining. As the price of natural gas fluctuates quite a lot across the globe, so too does the estimated cost of hydrogen, ranging from around $1 per kilogram in the United States to over $2 in Australia to sometimes close to $4 per kilogram in Europe. Particularly in these high-price regions, these capital-intense industries are seeking suitable replacements for fossil fuel-derived hydrogen that also meet their strict operational requirements. In other words, clean hydrogen technologies need to match the large scale of existing industrial facilities and operate around the clock, even when using renewable energy sources. Our proprietary technology does just that, while also enabling the capture of CO2 for further emissions reduction. We hold the exclusive licenses to the patents filed from Caltech for both the water splitting and CO2 capture technologies. With 2 additional developments filed since our founding, our patent portfolio represents a strong IP moat. And we also enjoy the luxury of choice when optimizing our monetization strategy, depending on investor sentiment. On the one hand, we can seek faster returns with an asset-light, license-only approach, or we can seek long-term maximal returns by building and deploying hydrogen production plants ourselves. For now, we are pursuing a combination of the two, licensing the technology to strategic partners while remaining hands-on in the technology advancement through joint development agreements. So where are we and where are we going? Since our founding in 2022, we have completed verification through batch processes, and we are now well on our way to building to continuous scale, having fabricated and tested isolated continuous flow reactors at our facilities in Southern California. We are finalizing the build-out and integration of these continuous scale unit operations in advance of piloting our technology, for which we've engaged with Southwest Research Institute for front-end engineering design. To complete that scale-up work, we are excited at the opportunity to partner with Halliburton Labs, particularly on aspects like improving our process design and the sourcing of materials and equipment through supply chain support. We are actively seeking investment partners now, and I invite you to reach out anytime with inquiries. On behalf of the HGenium team, I would like to thank Halliburton Labs for this opportunity to introduce our company and to share our novel carbon-negative hydrogen technology that is changing the way for producing clean feedstocks for clean hydrocarbons.
So first question is, oh, no, go ahead. I thought, go ahead, sorry.
Go Beavers. Really exciting ideas here. Talk to us about the projected economics of the hydrogen chemistry process.
Yeah, that's the first question we always get. That's what people want to know. What's the levelized cost of hydrogen? And short answer, it's less than $3 a kilogram at nth of a kind scale. There's assumptions there on energy costs, particularly energy storage costs. Those are the 2 real levers that we can play with for costs that affect our levelized costs. What also is a big factor is what we could sell that CO2 for, right? Because we are pulling it out of the ground. That does assume that pulling it out of the air. That does assume that there's some value there too. So those are kind of the offsetting factors, but we look at less than $3 a kilogram.
Back on the cost curve here, what are the key drivers to your costs? Is it CapEx, kind of the energy source, feedstock? What is it?
Yeah, it's primarily cost of energy and cost of storage, right? One of the big advantages of using heat, as I said in the video, is that we can run all the time because heat's a lot easier to store than electricity. But that does mean you have to have 16, 18 hours of storage in order to be able to handle strange weather events. So having something that large as a thermal energy backup system is going to be is a cost contributor. The other aspects of cost of energy, we assume in our economics solar PV plus resistive heating as our source of heat. That is only because that's the way that we can reach the temperatures that we want to hit right now. If there's other companies that are working on it, and we just saw one, then we're going to be ready for them. And we're looking forward to be able to partner with heat companies to do that.
But right now, big players are cost of heat and cost of storage.
Thanks, Nate. What dependencies on public-private infrastructure do you anticipate for transporting water to and from the plant?
I love it when people ask about water because that's a place that we really get to set ourselves apart from electrolysis. We don't need really high quality water to run our plant because we turn it into steam anyway. So you could say you need to have an installation in the desert because that's where there's clean PV or clean wind, but we don't need to have a lot of infrastructure in place in order to do any of that water treatment. In theory, actually, and we've done some preliminary testing, although it's not part of our end process, we could use salt water. Solar thermal desal is something that it's a viable technology. It's not what we use, right? We use reverse osmosis, but all we need is steam. And so if you're able to boil off that water from seawater, we'd be able to use it too. So we actually don't rely that much on water infrastructure.
With respect to your technology, what is the key technology underpinning your patents? If you could just kind of tell us a little bit of what that technology unlock is.
Yeah, so we actually own patents for the chemical reaction. So if you want to have a production process that uses these materials, and it's a family of materials, it's not just the one reaction, we own the patent for, or we have an exclusive license to that patent. So if that's the real protection that we have, that's the real technological unlock, is that the combination of these kind of solid gas reactions executed in this way allows us to drop the temperature way down. I'm going to feel silly talking thermochemical water splitting with Will on the panel, but there's sorry, I lost track a little bit. Repeat what you indicated. Oh, yeah, thank you. Yeah, the big thing is that we own the licenses to the chemical reactions themselves, and so we're highly protected in that way. Thank you. Long story short.
So the hydrogen at SMR, like you said, is $1 per kilogram. So it's difficult to see $3 per kilogram nth of a kind being cost competitive. So can you talk about what the cost is on the first of a kind, and specifically talk about hydrogen in kilowatt hour per kilogram and the carbon in kind of kilowatt hour per ton, so we can compare and contrast with what's out in the market?
So I'll have to get back to you on the energy per ton for the CO2, because that's largely a factor of the size of the air contactor that you would need for our plant, and I don't know that number offhand. Roughly speaking, from thermodynamic balancing, it's about 150-ish kilowatt hours per kilogram hydrogen. The reason that number sounds really high compared to electrolysis is we start with heat, not electricity, but that's the idea. And then to your first question, first of a kind was we're looking around probably $10 to $12 per kilogram. I mean, and again, it depends on what we would sell that CO2 for, or if even the first partner would want that CO2 capture as a piece of it.
So Nate, we got another minute, so I'm going to squeeze in a question myself, and I'm going to kind of piggyback on Rajesh's question on the economics. So you showed on the video the map of kind of the cost. The cost of gray hydrogen is a function of the cost of natural gas, basically, right? So given the delta in the different geographies, where do you see the opportunities as to where this could be economical, right? Because I mean, the way that I think about it is, hey, nat gas in the U.S., dirt cheap. It's hard to compete against that. But how do you think about the economics in other places around the world, and what do you think are the challenges operationally or otherwise of going there?
Yeah, that's an excellent question, and that's one that we're actively pursuing. So the one real exciting market we have that we're looking at is Japan, right? They're very much looking forward on hydrogen as a way to ensure their own domestic fuel supply. And so there's opportunities there, and they're also similarly ambitious to the U.S. in nuclear technologies, and that would be another way for us to be able to have that high quality heat that we would need. So that's a real target economy for us too. There's a bunch of others, but that's definitely one we're looking at.
Great. Thank you so much, Nate. Thanks for being here with us today. We're going to take a break, but before we do, there is something that we wanted to highlight. There are over 700 people that registered for this event today. We are super excited about what we've built. And hey, this would not be possible without Scott Gale. I love the man. Didn't thought I was going to get emotional, but hey. So Scott founded HalLabs Labs. He was a friend to many in the community here. We are announcing this award in Scott's memory, alongside with the Idea Village in New Orleans, for people who, like him, are making a real difference in the ecosystem we're building here in the Gulf Coast. So, sorry, I'm getting emotional. I did not expect this, but Scott was awesome.
You can't put it any better than that, Andreas. Scott was awesome person. He loved Halliburton, family man. Loved within not only Halliburton but the industry, and made a serious impact on people's lives. So, beautiful words, Andreas.
Thanks, Josh. On a less sentimental note, let's take a 20-minute break and see if I can pull myself back together. Okay. All right, everyone. We're back. I'm back, I think. So thank you. We're gonna get back on with the show, and we'll jump right into it. So we got Sam Kernion, CEO of CorePower Magnetics, joining us here on stage. Sam, please coming over.
Hi, everyone. My name is Sam Kernion, CEO for CorePower Magnetics. I want to first thank HalLabs Labs for the opportunity to pitch today. We're excited about what a partnership could bring.
CorePower is a Pittsburgh-based Carnegie Mellon spinout founded in June of 2020. We like to say we're driving magnetification forward, focusing on a critical part of the electrification movement that's often overlooked. The world is electrifying at an unprecedented rate, leading to an expected doubling of demand by 2050. Data centers, EVs, industrial expansion, all are straining our grid infrastructure while generation is becoming more distributed and complex. However, regardless of where electricity comes from or how it's used, every electron passes through multiple magnetic components. When people hear magnetic components, they often think of permanent magnets, especially rare earth magnets. And yes, we have exciting solutions to reduce rare earth dependence, but we need to think broader, especially about magnetics and power electronics. So while semiconductors have seen massive innovation, magnetic components have not kept pace and have become a huge bottleneck. Just as advanced semiconductors unlock the AI revolution, next generation magnetics are key to maximizing the impact of every electron. To meet this moment, CorePower is commercializing novel inductor, transformer, and motor technology that results in massive size reductions and improvements to efficiency, and in the case of motors, without the need for rare earth elements. We do this with a combination of proprietary nanocrystalline materials, processing, and component assembly for a simple and lean manufacturing pathway that enables us to redefine the limits of what these components can do. A great example of the breadth of the impact of this technology can be seen with data centers, where they are pretty much everywhere, from amorphous metal distribution transformers, medium frequency components and power conditioning, to the motors that consume so much of the energy and cooling systems. Applying CorePower components across a data center can result in massive efficiency gains and cost savings, or more of the energy going to the actual work. Data centers are just one part of the overall market. We're leading with the medium frequency passes because of the faster time to market and the urgency we see with power electronics applications. The commercial interactions also build the relationships and proven performance that can then be directly applied to motor commercialization. The team bringing this to market is rich in industry experience and expertise. I spent nearly a decade in the specialty alloy industry, working in R&D and leading large operations teams across markets such as energy and aerospace. Paul, our CTO and co-founder, while at NETL, took the technology we began at CMU and together with Kevin Byerly advanced it to the point of commercialization. Paul has since emerged as the leading domestic expert in soft magnetics. So now that you know a little bit about us, I want to tell you about where we are and where we're going. The company has raised approximately $10 million in funding, with only $3 million of it being dilutive. To scale quickly, we knew we needed to demonstrate both product capability and manufacturing capacity, qualified to industry standards. So in March of 2023, we set out to establish our manufacturing line and get our products into customers' hands. Our facility process capability starts with planar flow casting, which has our alloys essentially painted onto a copper wheel spinning at 60 miles an hour. This cools the material at over 1 million degrees per second to lock in the atomic structure we need for performance. But importantly, it also eliminates many of the traditional steelmaking steps, substantially reducing CapEx and OpEx. The second step is an inline annealing technique that is part of our foundational IP, providing unprecedented control of the magnetization process that reduces hotspots and enables thermal management no one else can do. Finally, we assemble into the final component, which looks, feels, and connects the same way as what our customers are used to, but with size and efficiency benefits that our tech enables. The facility has a revenue capacity of around $10 million. And with its opening about 6 months ago, our ability to deliver product to customers at commercial scale has changed the game on customer interactions. With land and expand focus on the large strategics and increased marketing efforts, we've seen our funnel balloon from a few million to over 50 million. Qualifications, exemplified by the 3 shown here, show our wide coverage in applications, and we are a short time away from full qualification or repeat orders, with more coming down the pipeline. We are now focused on ensuring we capitalize on the momentum. We have key elements in place, including talent pipelines and additional DOE funding that was based on the domestic need to solve the massive lead time issues we're currently seeing with distribution transformers. We'd love to have Halliburton support as we scale operations, leveraging your deep expertise in manufacturing, engineering, and supply chain, supporting large sites. Your capabilities, along with your connections in key energy-related markets like data centers, would be invaluable in helping us establish a dominant position in this space. Rising power demand and distributed systems require magnetics that scale. CorePower delivers with efficient, power-dense solutions built for next-gen power electronics. We're raising $8 million now to reach income positive with strong recurring revenue by 2027. Thank you for the time today, and we're looking forward to your questions.
So we got to see a little bit on the markets there that you can address. Can you give us a little bit of flavor on the applications, EVs? I saw data centers, aerospace, and what are most ready for the deployment? And then how do you adapt your technologies across those different use cases?
Yeah, thank you. Thanks for the question. Thank you for having me here today. Yeah, one of the great things about our potential is that magnetics are really everywhere. So that is it's a good problem to have, is that we have to find that right application to go into first. So we focus on power electronics applications. Think uninterruptible power supplies for data centers, active harmonic filters, just to name a couple. And we'll be looking to get into motors, starting with stationary, then looking into EVs. Obviously, transportation is difficult to get into. It's also beach up on cost quite a bit as well, but it's also one of the highest potential markets, so we see that coming in the future as well.
Can you tell us about your current production throughput and what's about your expansion plans moving forward?
Sure. Yeah. So our existing facility that was funded through ARPA-E Scale-Up has around 10 million a year in revenue potential. That corresponds roughly to around 10,000 parts of components that we can produce, transformers and inductors, at kind of the base modular size. We have another $20 million from the DOE, from the Manufacturing Energy Supply Chain Office, that we're looking to scale up to 10,000 metric tons of the metal per year. And with that, then we'll start getting more into the hundreds of thousands of components. Through 2030, our revenue projections get into those hundreds of millions, and eventually, if we're not exited by that point, into the 2030s, more into the billions of revenue, all just from that facility.
Nice job, thank you. Can you explain where in the value chain you're positioning? Are you a component supplier? Are you doing to an OEM? Are you doing systems? And will that value chain strategy vary by application?
Yeah, that's a great question. Right now, we are a component supplier. So we are selling the transformers and inductors that go into these systems. They're wired parts. And so our customers, it looks, feels, touches the same, but it's smaller and more efficient, so they can just install it directly in the system. We feel like that was really important. There hasn't been a lot of innovation in this space over the years because of that disconnect between material science and electrical engineering. And by doing that at the beginning, we can get that momentum. But as we grow, we do see the outsourcing of the component assembly process being very likely. There's a lot of value in the IP and controlling that, but the actual process of doing that is not that much value add at that point once you're at higher volume. And especially with motors or rotating part, there's a lot of tier ones that are already doing this with qualifications that it would allow us to accelerate our time to market.
If I understand right, the core seems to be a nanocrystalline material.
Correct.
Versus a lot of materials used across inductors, transformers, motors. If you have a table of parameters like permeability, all of that stuff, what market would you really want to go after? Would you excel at? What product would you excel at? And where would you not want to go? I mean, it's a large enough market, you don't need to go after everything. What can you do? What can you not do?
Yeah, that's a great question as well. So we're focused really on the higher power electronics right now, where folks on the semiconductor side, think of like Infineon, is going to push into the hundreds of kilowatts in terms of some of the modules that they're going after for data centers. We feel like we have a really strong play there because they're going into the higher frequencies, and those higher power levels tend to cause a lot of thermal issues with the existing metals that are out there. With our components, we can keep them cool. The permeability is a really key differentiating aspect for us. We can control it throughout the core. And so that image that was on the screen before, we can prevent that hot spot from forming on the inner diameter that nobody else can do. And so we feel like that really has a strong value proposition for us. Motors in the future, again, it's just a more difficult qualification pathway, but obviously efficiency is so huge for things like range for vehicles, and that's where we also see a really strong value proposition. Thank you.
I want to tease out a little bit on the value to your customers. So I think you commented on thermal uniformity, so more of a reliability, and you also commented on the density. Can you help us understand what are the #1 requirements by your customers now?
Yeah, right now we have a lot of customers who come to us and they have the system already designed and they have this small area they're trying to fit the magnetics within. And all of that is a combination of size, temperature, efficiency that they've considered and hoping that they could get a magnetic component. And usually we're the only ones who actually provide that component within that size volume without them having to redesign that system. So it is a combination. It's typically size, temperature, and it kind of depends on what they're looking for. But at the end of the day, they're trying to ship that product. There's a lot of urgency behind it. And so the fact that we can provide that and also give them something that's pre-certified and standardized in the future, which they don't have an option for right now with these power levels.
For the size reduction, quantitatively, how much are we talking about?
It does depend on the system, but typically a 2x reduction is possible. Yeah.
Very good. Sam, I'm going to jump in and squeeze in 2 questions. The first one is in terms of physical scale, as you think about moving up dimensionally to larger scale applications, what are the engineering challenges in scaling that?
Yeah, great question as well. The technology is great from a modular standpoint to line up with where we see our customers also having the same modular level. So you might see a UPS in a data center that is over a megawatt, but within that UPS, you'll have 125 kilowatt to 150 kilowatt modules. And our cores, basically just a couple of them, would be able to provide that same level of power. And though it kind of looks like a roll of Scotch tape, and so you can kind of stack them up as needed to get to those levels as well.
Very good. And one other one from my end on the so kind of freeing from rare earths is a great angle, right? And a really smart play from a national security standpoint, from a supply chain standpoint. But what other minerals fit in your model that are not domestic that still need to be thought of in terms of actually building the value chain for this?
Yeah, absolutely. So there's only 3 really main ferromagnetic elements: iron, nickel, and cobalt. Cobalt's obviously the one that has the most supply chain risk there. When we do add that gives us the highest value proposition, so we can offset the price that way. We've done the sensitivity analysis on that we can still get to the 50% margins that we've targeted, even at our most premium grade. Niobium's also a big one for nanocrystalline alloys, and most of that is in Brazil. The good thing about niobium too, though, it's used in a number of different alloy systems outside of magnetics, super alloys being a big one, and just high strength steels as well. So there's overall a national interest to make sure that we maintain that. Canada also has some up there as well, but that's also a minor part of our alloy system, so it's not as big of a deal.
Excellent. Thank you so much, Sam. Thank you for being with us today. It's great
you.
spending time with you.
Appreciate it.
Okay. Before we go on, we're going to share one more success story from one of our companies. Will Tope's here with us all the way from Lancashire, UK. He made it. His luggage did not, but Lululemon outfitted him for the day. So, Will, thank you for being here with us today, and let's hear some more about where Lena's at these days.
Who are we? We are a group of crazy individuals who've taken the cutting edge of materials science and decided to use it to build a battery literally made out of salt, and the result is something that performs like nothing else in the market.
We are taking a chemistry that's been around since the 1980s. We're re-engineering the cell, re-engineering quite how you put the cell together and the configuration, using some modern material science and engineering, putting it together in a new way, which really kind of unlocks its potential.
So not only is our battery made out of abundant raw materials, quite literally salt, it can withstand even the harshest conditions. So our partners can finally deploy a battery alongside some of the greatest solar opportunities in the world, whether that be in a desert, whether that be in a rooftop in Mumbai, and turn that solar into a steady flow of low-cost electrons into compute, into industry, into our growing communities all around the world.
I think that the tantalizing prospect of a new technology, newly developed and newly deployed by us, is the drive.
The science in and of itself is interesting, whether that's the underlying technology of the batteries or the materials science that underpins everything.
It's a company that challenges on the day-to-day, not only with the technology, but the people as well. It makes you want to bring your A game.
Everyone is a little bit different, and I just love that variety in the people, but it's all like one whole team together, and it's just great, lovely, easy to work here.
The whole team is very invested in every single area of this excitement. It's quite interesting to see like that people at different departments are always chiming in into other things and wanting to know and being very, very interested. I think that's a big part of why I want to come to work every single day.
There's always something new going on where we're developing the technology that we've got. There's always new processes to learn.
Every experiment that we make is meant to give us answers. Even if it doesn't go in the positive direction, it always tells us what doesn't work or what works. So it's always positive attitude.
It helps the process enormously to feel like you're working together towards a particular scientific goal.
I think there's very few opportunities in life where you're able to work on a product that has a genuine application, a scale-up process that allows you to take something from the lab through to manufacturing, and a core set of people that are brilliant to work with.
I think I belong to one of the first generations in which the climate change was taught in schools. So I've always been aware of it since a very young age. So being part of the technology that might change the way that the global energy is consumed and try to mitigate these challenges with climate change is very exciting.
I love that video. It also helps that the videographer was working with preschoolers like the week before, so I think it really got her in the right mode to work with a bunch of scientists. But watching that, it reminds me, it feels like yesterday, about just over 2 years ago, the Halliburton Lab team found us as a small company based in the very north of England, almost bordering Scotland, with this incredible IP and idea and a huge amount of ambition. And we joined the program, and I was thinking the program is a lot like having a mentor, a corporate mentor. And like every good mentorship relationship, over time, you try to emulate what it is that your mentor does really, really well. And for us, that meant this conviction to try and replicate Halliburton's focus,
their execution capability, and their efficiency. And it was through that, over the past 2 years, that has had a huge impact on our success. So from that 2 years ago, we've now grown the team to over 35 people. We have built a first-of-a-kind manufacturing line in the UK to make our batteries. And most importantly, we've taken our batteries and deployed them in projects with real customers all around the world. We've had projects in Mumbai and Delhi, and we just started cycling in Saudi Arabia. So for me, I'm just hugely appreciative that of all the companies that could have come and been our big brother, it was Halliburton, and it was Halliburton that defined what good looked like. I think without them, we probably would have wasted a bunch of money, which I'm glad we didn't, and it kept us focused on what mattered. So for everyone who's pitching, I think good luck. I'm obviously biased, but I don't think you could be bidding for a better program. And to the Halliburton Labs team and to Naviscale as well, who are up at the back, a huge thank you, but fair warning, I'm not done asking for your support just yet. I'm on year 3, and I'm going to keep asking. So you're not getting rid of us just yet.
Well, it's great to have you here. It's great to see the success that you're having. We've talked about it, but congratulations on the ribbon cutting and having the plant going. It's cool to see a Lena logo next to a Tata logo. That's a huge deal. So congratulations. Thank you. All right. On that cheerful note, next up we have Howard Yu. Howard's the CEO of Tidal Metals. He's going to be joining here us on stage. Howard.
Hello, I'm Howard, CEO and co-founder of Tidal Metals. Our mission is to create enough decarbonized magnesium to move the needle on climate change. 4 gigatons of vehicles emit 8 gigatons of carbon dioxide every year, a quarter of all emissions. Magnesium is the lightest structural metal. It is 4.5 times lighter than steel. No matter how they are powered, our cars could emit gigatons less if they are lighter. You already use magnesium. It's in cars, planes, laptops, tools, bikes, and more. You need magnesium to make aluminum alloys, steel for the defense industry, and titanium. You also need it for fighters, missiles, helicopters, and most national defense platforms. Tidal Metals will fix magnesium's 3 big problems: supply chain sovereignty, carbon intensity, and fast scaling. The US has lost all its production of new magnesium. China dominates with 91% of global production because they have been the cheapest. We will compete by co-producing chlorine with our magnesium. Producing 2 products with 1 process creates unassailable unit economics. Magnesium produced in China is so carbon intensive, it negates much of the emission savings from lightweighting. We have created an electrified process that can be easily decarbonized. Climate solutions must scale fast. Digging up rocks is not the fastest way. We use seawater, the biggest source of magnesium. Seawater contains a near infinite amount of magnesium. There is a pound in every 92 gallons. The amount of magnesium uncaptured in desalination brine is 100 times the amount we produce. Our process can be combined with desalination to generate water, magnesium, and chlorine. Ethan, Kevin, and I are all PhD physicists with over 20 years of deep tech experience. In the 8 years since we co-founded Tidal Metals, we have successfully led the development, manufacturing, and testing of our patented technologies. Our CFO, Duncan, has held senior leadership positions for more than 30 years. Our talented team now numbers 23. We have raised both public and private funding, including $4 million across 9 grants and $9 million of private investments. Our venture lead is the top-tier deep tech fund, DCVC. We intend to continue this funding strategy for our commercial plan. Congress just appropriated $8 billion to reshore critical minerals. We have spoken to dozens of officials to secure grant funding. We are building a 10-ton per year pilot plant that will demonstrate every process required to make magnesium from seawater. The first step uses modern nanofiltration membranes to concentrate seawater into a magnesium chloride brine. This image shows the scale up from our membrane lab on the left to the larger pilot plant on the right. Our patented vapor pump can fractionally crystallize pure magnesium chloride salt, leaving all the impurities in solution. This purity is crucially important. I'm showing some sample pieces as we manufacture this in-house to protect our IP beyond patents and trade secrets. In this video inset, you can see Tomas executing a robotic laser weld. We then dehydrate the salt using the best technology to ensure full dehydration, a fluidized bed dryer using hydrogen chloride as the drying gas. Our crystallizer technology is used again here to help solve a challenging task, dewatering the drying gas. Finally, our pure and fully dehydrated magnesium chloride is melted and electrolyzed into magnesium metal and chlorine using electricity. We are modernizing this mature technology. Our demo plant will mostly complete construction by the end of the year. The only inputs are electricity and seawater, so using decarbonized electricity produces decarbonized metal. The front and back halves of a commercial plant can be separated because magnesium chloride is safe and easy to transport. Our early go-to-market strategy focuses on buyers who need domestic magnesium. They make magnesium powders and alloys, aluminum alloys, and steel desulfurization products. We're negotiating an MOU for a joint venture with a chlorine channel partner. On the input side, we're discussing using brine from a desalination project. Tidal Metals will soon disrupt lightweight metals, starting with magnesium, then titanium. If you don't think Halliburton can accelerate a metals company, I ask who else makes equipment for pumping large volumes of salt brines and slurries, can design control systems for manufacturing at scale, and has expertise in corrosive liquids and gases at high temperatures. Halliburton is actually a perfect partner. We would be thrilled to join the next cohort. Thank you.
Thanks, Howard. Thanks for being here with us. What are some of your process bottlenecks now? Is it on the chemistry side, engineering, supply chain, and automation? And how do you see that changing as you scale?
Thank you. Great to be here today. Thank you for the question. Our biggest bottleneck is definitely engineering. It's not chemistry because we've actually gotten rid of all of the chemistry. It's saved tremendously on cost. What we are doing is bringing back technologies like electrolysis and our own patented crystallization technology. The engineering pathway to scaling up is the big challenge that we face. Fortunately, what was a bottleneck will become a moat for us. That technology is mature, but forgotten in the US. Once we rebuilt it, we will have the expertise to scale.
Very nice job, Howard. So China dominates the magnesium industry. What is China doing innovatively with magnesium that could foreshadow the kind of innovations we could see with magnesium here in the US and Europe?
Thanks for that question, Earl. The Chinese have taken the lead in magnesium innovation throughout the world. Their strategy is to build magnesium into the next generation of electric vehicles and become the dominant producer around the world. I am seeing 100-pound magnesium Thixel molded parts being made in China out of new alloys that they plan to take over the global car market. Because they own the battery space, the rare earth space, and the magnesium space, they'll be able to make a car that's lighter and cheaper than everyone else. Thixel molding is a technology that they're using at large scale, and that's using magnesium chips and extruding them in a heated screw press, a lot like plastic injection molding. This is superior to aluminum gigacasting, and they plan on sort of owning this space.
How do you compare your economics from selling magnesium versus chlorine, and compare that with the chlor-alkali process today in terms of how you're doing on the electrolysis side of things?
Thanks for that analogy. Magnesium has traditionally been a single product company. Dow, China, most producers make magnesium alone. We have spent 30 years trying to beat them at their own game. We can't do it. So while we can compete directly with China on production costs, our secret is that we are more like chlor-alkali in that we extract magnesium chloride directly from seawater, separate it, and get two valuable products to sell. So 1 unit of separation, using the chlor-alkali terminology, gives us 1 ton of magnesium and 2.9 tons of chlorine. That 2.9 tons of chlorine forms the basis of a byproduct value that is so high that it essentially covers most of our production cost. When I say we have unassailable unit economics, what I really mean is we don't really need to sell the magnesium to stay in business. Now, granted, that magnesium is a very high value product. A metric ton of magnesium in the United States is worth $5,500.
For the unit economics to work that you just mentioned, what kind of lifetime are you assuming? You're using seawater, lots of impurities, and where are you at now in terms of the technology de-risking in terms of lifetime?
Thanks for that. So as part of the techno-economic analysis we actually are very conservative with replacement parts. The dominant replacement parts we need are membranes on the front end and the entire electrolyzer cell on the back end. Traditionally, electrolyzer cells have only lasted about 3 years, and that's using 50-year-old technology. We have a multi-generational product plan to bring today's technologies to bear on molten salt technology. But even in these analysis, we've been extremely conservative and only estimate a 3-year life on that. So where we come in is we are building a modular system where we anticipate a lot of modular electrolysis plants sort of dotted where there is renewable energy or there is offtake for the chlorine. And because of that modularity, we can actually remanufacture and improve our electrolyzer designs as they wear out.
And you assume 3 years, and where are you at now using seawater as input?
The seawater and the electrolyzer is sort of decoupled from that. It uses, by producing the purest feedstock that's ever been used in an electrolyzer, we hope that the electrolyzer is actually lasts much longer than traditionally has happened. On the front end where the membranes touch the seawater, that's actually very mature technology. Nanofiltration has been used for over a decade, and those lifetimes are well known, typically 2 to 5 years.
What regulatory or environmental permitting challenges do you expect? I'm really interested around water rights, discharge, marine ecology, and then the brine. How do you actually dispose of the brine?
So, great question. Our process actually doesn't produce a brine. If we were not to produce fresh water, we are actually directly extracting just the magnesium chloride. In fact, when we talk to desalination companies, for example, we were talking with Tampa, they actually want to reduce the salt load that they put into their brine. So we're actually doing them a synergistic activity by removing salinity out of the water. When we do produce fresh water, that effect has the same thing. That said, even when we discharge a water that is reduced in salinity, it is a novel process. We've begun the process with talking to a lot of regulatory bodies, and we anticipate that work will be complete in 12 months.
Excellent. Howard, thank you so much for sharing Tidal with us and for this great update. We're right at 7 minutes. This picture perfect. So thank you so much.
Thank you.
Okay, with that, next up we have Ben Tarbell. Ben is the CEO of Ebb Carbon. Please join us on stage, Ben.
Hi, I'm Ben Tarbell, co-founder and CEO of Ebb. Thank you for the opportunity to share what we're building. Ebb is a water technology company based in South San Francisco, pioneering an electrochemical process that turns industrial brine into value. Today, demand for fresh water is skyrocketing, and desalination has become critical to meeting that need. There are over 16,000 coastal desalination plants worldwide, but every day, these plants discharge 50 million tons of concentrated brine into the ocean, harming ecosystems and limiting the industry's growth. At Ebb, we see that brine not as a liability, but as an opportunity. Our technology transforms this waste into multiple sources of value, creating a $75 billion opportunity. Our patented system does three things. First, it boosts freshwater output by more than 15% from existing plants. Second, it enables gigaton-scale carbon removal at costs under $100 per ton. And third, it produces valuable industrial co-products like caustic soda at less than $200 per ton. This is all made possible by our modular, low-energy technology, protected by a growing IP portfolio with more than a dozen filings and 3 U.S. patents. By aligning with established industries desalination, decarbonization, and chemicals, Ebb has a clear pathway to growth and scale. Here's how it works. Our system plugs directly into desalination plants. We take their brine waste and run it through electrochemical membranes, which separates it into 3 outputs. A lower salinity stream that is recycled back to the plant to generate additional fresh water, industrial acids and bases for commodity markets, and a safe alkaline stream that returns to the ocean where it unlocks durable CO2 removal and storage. 1 waste feedstock, 3 valuable products, all delivered through Ebb's technology. We've been at this for nearly 4 years. In that time, we've moved from prototypes to pilots, secured offtake agreements with Microsoft and Stripe, and signed partnerships with leading desalination operators. Alongside these milestones, we've built the foundations of our business model. Ebb brings the technology and secures offtake contracts. Our partners provide sites, expertise, and capital investment. Together, we co-develop projects that generate multiple cash flows, fresh water, carbon credits, and industrial chemicals. This delivers strong project IRRs above 20% today and can evolve into a high-margin licensing model. For over 2 years, we've operated a 100-ton pilot at the Department of Energy's Pacific Northwest National Lab in partnership with NOAA and the University of Washington. This public-private partnership has produced peer-reviewed publications showing our approach is both safe and effective. We've demonstrated that we can safely deliver alkalinity into the ocean, draw down CO2, and verify durable carbon removal, all in open collaboration with independent scientific partners. We've now scaled to Project Makoma, a larger system operating in Port Angeles, Washington. It's our first commercial-scale pilot, delivering carbon removals while also demonstrating desalination integration and validating water recovery. Building on this success, our next focus is scaling in the GCC, a region with the scale, infrastructure, and market conditions to accelerate Ebb's growth. The GCC is the ideal launchpad for scale. It holds 70% of global desalination capacity, has strong demand for carbon removal, and major industrial markets for co-products. We've signed with one of the world's largest desal operators and built a pipeline representing hundreds of megatons of capacity. With regional tailwinds in water security and clean energy, Ebb is positioned to scale rapidly, and Halliburton Labs can help accelerate that trajectory. Halliburton Labs is an ideal partner to accelerate all of this. The Halliburton team brings the expertise we need from market entry and commercial introductions to engineering design, cost modeling, and process controls. One area where your experience is especially valuable is validating our asset management pathways. Work with a third-party engineering firm has shown that we can dispose of excess acid for less than $10 per ton of CO2. But with Halliburton's expertise, we can refine and operationalize this approach and unlock new use cases that can yield additional revenue. Our leadership team has decades of experience scaling breakthrough technologies with track records at Tesla, SolarCity, Google, and SunPower. Many of us have worked together before, and we're backed by some of the most respected investors focused on the energy transition. Partnering with Halliburton Labs will accelerate our path from pilots to commercial scale, and we're excited to take that next step together.
Very nicely done. Can you talk to me about your co-products? Your economics depend on them, and I think you're going to have salty acids and bases. Tell me about the product specifications, and you're going to have a lot of acid to move. How are you going to get the valorization of those co-products out?
Yeah, so the unit economics do not depend on the co-products. The co-products are upside. We can do CDR at less than $100 a ton without selling water, without selling NaOH or HCl. And we sell contracts for CDR well above $1,000 a ton today. It will obviously decrease over time. We get a boost in the near term from selling the co-products. Water, 15% extra water production at a desal plant is significant. That's a significant boost in their profitability. And then we sell HCl and NaOH. The specs, we can turn knobs. We can trade off a little bit more energy to get more concentration, or we can buy additional water to make it pure. And so, you asking about the acid. The acid, in the long term, we're neutralizing it underground. At gigaton scale, we pump it into saline aquifers. It neutralizes in those aquifers. In the near term, we blend it with higher concentration acids and sell industrial commodities, 20% HCl. We can make a little bit of money doing that. In the medium term, this is where the opportunity space is. We're seeing a lot of traction with opportunities in things like mining, industrial wastes out of mining that are alkaline in nature. A salty acid mixed with those wastes helps solve a significant problem that the mining sector has. Similarly, carbon sequestration, there's methods of mineralization of CO2 underground. We can use our acid as the carrier fluid to inject the CO2. It also turns out that our acid helps accelerate those processes of mineralization and expand the capacity of that. But there's other opportunities that we're working on that Halliburton could help us accelerate.
Energy consumption has been the biggest challenge for DAC or DOC. So help us understand a little bit about your kilowatt hour per ton CO2, and to the extent you can compare with somebody like Captura or Equitic going after the same market.
Yeah, so we've chosen bipolar membrane electrodialysis for a reason. It's one of the lowest energy intensity pathways to creating this low concentration alkalinity. And so it's a scalable modular process that achieves one of the lowest energy intensities of any approach. One of the reasons that's possible is because instead of separating low concentration CO2 from the air, we're interacting with the high concentration salts. And so there's just a much, much lower energy intensity to do that. We've demonstrated around 1 megawatt hour per ton of CO2 in the lab. And this is a modular membrane technology that we've demonstrated scales quite easily from the lab. And then the comparison to other methods, we just don't have the energy intensity that they do. There's other processes, in some of those processes, they have to separate liquid and gas in a way that adds, very significant energy intensity that we just don't have.
The $100 a ton target is very attractive. What has to be true? What do you have to deliver on your technical milestones to get there?
So we've already demonstrated the energy intensity required to get there. What's left is scaling, and we get a lot of CapEx savings by scaling with desalination plants. They already bring the infrastructure in pumping, pretreatment, the infrastructure around power, roads, security. There's a lot of CapEx that we can piggyback off those plants. And so there's actually a very small minimum efficient scale for us because of the modularity. As we plug into the desal plants, we can grow modularly as we scale out, and we can achieve the cost savings we require through the shared infrastructure.
So your plan is to deploy these modules near existing salty water infrastructure. I'm wondering on the constraints that you face finding those sites, and then constraints on top of that. For example, consistent water flow, and then I'm piling on the questions here, but I'm back to the discharge of the alkalized water. Who owns that discharge stream? Is that the plant or you?
Yeah, so I'll try and get to all of those questions. But so the constraints around siting. So we've just recently signed with one of the largest desal owner operators in the world. Just one of their plants can accommodate 20 megatons of CDR. So this is an imminently scalable technology, within the existing infrastructure at a plant like that. I maybe missed the middle question, but the end question was around who owns the discharge. So these existing plants have permits around discharging the brine waste. The brine waste is a challenge for them. It creates an environmental hazard. It turns out that our process reduces the concentration of that brine waste significantly, so we can reduce that hazard. But we can fit within their permits. So they have a regulated pH range. We can fit within that permit. And certainly, we can do megaton scale within their permit. Over time, there's plenty of opportunity to adjust those permits, but we can achieve scale just within the existing permits. And if I missed a middle question, okay.
You good? Okay, we can squeeze in if we keep the answer very brief.
Yeah, I think you touched on this. What is the most significant hurdle in plugging into some of these plants? I think you were about to talk about that.
Yeah, I mean, so desal plants come from a utility industry. It's a critical infrastructure requirement, and so there's a lot of planning that goes in. But we operate at the discharge of their plant, so they already decided they were done with the brine. It's easy for us to take that waste and then we discharge downstream. So because we're downstream, the integration challenge is relatively small.
Very good. Ben, thank you so much for sharing Ebb's journey with us. Next up, we have Tim Fairley-Wax, Tim's the CEO of Aquora Biosystems.
The refining industry is preparing for the race to scale renewable fuels, and major players are making large investments to meet the soaring demand for sustainable aviation fuel, or SAF. But several bottlenecks like high feedstock and conversion costs threaten to ground this transition before it ever takes off. Hi, I'm Tim Fairley-Wax, the CEO of Aquora Biosystems, and our company is targeting these challenges by utilizing low-cost organic waste feedstocks in combination with low-energy conversion processes to produce SAF at scale. The reality is, the feedstocks of today, like used cooking oil or agricultural crops, cannot alone build the refineries of tomorrow. Their costs are volatile, their supply is limited, and their carbon intensity can only go so low. This creates significant risk for billion-dollar refinery conversions. But what if the next great feedstock opportunity isn't a crop to be grown, but a problem to be solved? Right now, America pays billions of dollars to throw away enough organic waste to produce over a third of our entire demand for aviation fuel. We see this not as waste, but as a vast, untapped domestic resource ready to be used. So what does Aquora do? We have a proprietary fermentation technology that upcycles low-value organic wastes, so things like food waste, manure, or industrial byproducts, into refinery-ready ketone intermediates. We don't make fuel, we make the high-quality feedstock that makes SAF cheaper to produce, lower in carbon, and de-linked from existing volatile supply chains. Our process overcomes the slow processing rates and low yields that plague today's fermentation approaches. Crucially, for our refining customers, our ketone intermediate is designed to be co-processed in existing hydrotreating units, for example, with fats, oils, and grease. Our product allows renewable fuel producers to increase throughput with minimal disruption to existing operations. The result is an ultra-negative carbon intensity fuel that will command premium pricing in low-carbon fuel markets. Aquora's approach to SAF is fundamentally different than what's done today. While others pursue complex, capital-intensive pathways that require entirely new refining units, we focus on a capital-light drop-in solution. While eSAF approaches can be 5 times the cost of fossil jet fuel, the organic waste fermentation pathway is already projected to be equal to the lowest cost SAF today, which is HEFA-SAF. And our innovations in conversion efficiency can further drive this cost down, aiming for cost parity with fossil jet fuel. Our proprietary fermentation is robust and can handle a wide variety of organic feedstocks, insulating us from the supply chain risks that are challenges for our competitors. This combination of feedstock flexibility and seamless integration into existing refining assets gives us a strong market advantage. So, what's the status of Aquora today? where we successfully validated our technology at the bench scale with the support of the Department of Energy and Argonne National Lab, where we currently have access to world-class lab resources. We have a soon-to-be-announced project funded by a potential customer for our downstream processing. We have also designed the ideal pilot project to prove our model and have already established key relationships with major food waste producers and have an LOI with a trusted EPC firm. Our team has the right blend of expertise to bridge the gap between biotechnology and the renewable fuels world. With decades of combined experience in bioprocess engineering, startup scaling, and the cultivated relationships with partners for downstream operations, we have the credibility and know-how to execute on this opportunity. Our team's core expertise is in biotechnology, but a key component of our successful business model is logistics. Specifically, we'll need to coordinate supplier networks to transport many types of organic waste to receiving facilities at our biorefineries. We'll also need to figure out how to get our ketone products safely and efficiently transported to nearby refineries for hydrotreating. With Halliburton's partnership, we can solve these challenges by leveraging Halliburton's expertise in managing supplier networks and complicated chemical transport logistics. Accessing this operational knowledge allows us to avoid common pitfalls and build a resilient, scalable, and profitable business that is ready for major refinery partnerships. Our immediate goal is to launch our first pilot, proving our model at scale. But our vision is much bigger. We are here seeking strategic partners who will help us deploy this technology at scale. We are looking for champions within the Halliburton ecosystem who can bring not just the capital, but the critical expertise in engineering, project execution, and customer relationships to Aquora's mission. We believe that the future of renewable fuels is with new feedstocks, and Aquora's approach is crucial to building a resilient and truly scalable supply chain for renewable fuels here in America as well as abroad. We have the technology, refiners have the infrastructure, so let's work together to reimagine fuel production of the future. Thank you.
It's an important area. How do you compare the cost? I know you had a chart, but something like Lanza's alcohol to jet is already closer to HEFA, and that will only go down because they're starting to scale up. How do you compare your cost today in the first of a kind, and then how would that go down nth of a kind?
Yeah, absolutely. So just to be fair, I took the Rocky Mountain Institute's estimation for all the other pathways to set a baseline and use cost projections from NREL and Argonne National Lab on those fuel pricing, just to standard that. But you're right, as they scale, those costs may come down. If you look at today at like Lanza Jet's alcohol to jet fuel facility, I think it's about a $200 million CapEx facility with about 10 million gallons of output. If you project what we're doing for that same $200 million input, we could get about 25 to 30 million gallons of output. And so because of that, already on a CapEx side, we're 2.5 to 3x lower there. We're also using a low temperature biological conversion for a large portion of our processing. That drives down our OpEx, relative to these high temperature thermocatalytic approaches that other pathways are doing.
To clarify, what is your end product and what's the final SAF product? Who makes it?
Yeah, absolutely. So we're targeting as early adopters, just co-processing our ketone product. So this is a C10 to C16 product with existing fats, oil, and greases going to HEFA facilities. Those facilities right now are seeing increasing feedstock costs. They're looking for new ways to use that infrastructure. And that way at Aquora, we're not building out that refining infrastructure ourselves. So a more capital light approach than some of these other SAF companies.
Great presentation. One of the major requirements for chemical production is consistency. And with your input being waste and highly volatile and variable, how will you be adjusting your process to ensure a consistent product?
Yeah, fantastic question. So we've had years of experience processing real food waste and real sewage sludge, so we know the variability question. There's basically two ways to get over this. We do newer sensing. So typical anaerobic digesters, they have pH and like biogas flow, and that's all they do. The precision fermentation industry has gotten things a lot better about sensing your inputs and what's in your reactors. And we're using spectroscopy tools for inline probes to know what's our proteins, lipids, carbs coming into our reactor, what's in there, and what's being processed. The second is working with partners on pre-processing technologies for particularly challenging feedstocks like a manure. They can create completely soluble feeds. That's great for our microbes to use, and it's a much more consistent feedstock. And so for these feedstocks, we've already done the energy balances on those pre-processing technologies. They look great if you're using a concentrated feedstock, which we would be using for these biorefineries.
I'm wondering about energy consumption. So maybe you can detail that on per unit of biofuel produced compared to conventional biofuel methods.
Yeah, absolutely. So I'm my background's in wastewater process engineering, so I know that space the best. So on our fermentation side, we're literally using on the order of like a kilowatt per meter cubed of feedstock process. This is like a 35 Celsius fermentation with high heat recovery. You're not putting much energy into that. We're partnering with NREL for the downstream ketonization piece. They're operating their thermocatalytic reactors right now at about 300 to 400 degrees Celsius, depending on their conversion catalyst that they're using. That process is in line with the temperature you would see in a lot of other thermocatalytic upgrading. Compared to other processes, on like an ESAF basis, and I don't know the energy input per gallon, but you are trying to turn a molecule that has no electrons, CO2, into a molecule that has C10 to C16. You're pumping in a lot of electrons to do that. We're not doing that. We're using biology to do that conversion for us.
Can you speak to some of the partnerships that are critical for scaling up, and where are you in conversations with some of those?
Yeah, so I think along the value chain, there's several key partnerships. So in feedstocks, we've already engaged with some of the largest waste producers. These are like the large grocery producers. They're right now having contracts with like a waste management to send their feedstock to a landfill. They have priorities to divert from landfills, and so they want to work with people who can do that at scale. So that's on the feedstock side. On the EPC side, that's really, really key to our scaling. We're working with people in the anaerobic digestion industry who know how to process these wastes. And then on the downstream side, so I think on the fermentation side, we've proven the technology at scale, and now it's engineering, scale-up, and optimization work. On the ketonization side, as I mentioned, we're working with some folks at NREL who developed this technology. There's kind of one, I guess, main question on the ketonization side is like, are we going to use chemical engineering catalyst reactors or fuel catalyst reactors? And so then it's finding the right partners. It's basically the right EPCs and the right metallurgy scientists to understand what's going to be the best for that scaling.
Very nicely done. Thank you. What scale are you operating at, and what's your scale trajectory? And when you finally get to broad commercialization, what's your optimal scale?
Yeah, perfect question. So right now we're at a pre-pilot, so processing in like 10-liter bioreactors. Our next scale, we're looking to go to like a 1 ton per day feedstock, so using food waste at commercial scale. So when we think about commercial scale, we're going to use existing anaerobic digestion tank infrastructure. We don't want to redesign bespoke infrastructure for ourselves. These tanks are often about 1 million gallons. Basically, we'd use those, and then depending on how much feedstock is available, you just copy paste 1 million gallon tanks over and over again. This is what's already done in the anaerobic digestion infrastructure. If we take Houston as an example, I think they produce around 1 million tons of food waste a year. We could start with a facility that's taking a tenth of that and put in 2 digesters to do that.
So I'll put in a plug for Houston. There's a lot of people, a lot of biological waste, and a lot of refining capacity. So it sounds like a great place to do something like this. I will, however, throw in a question. So the announcement from Breakthrough here recently is an interesting tailwind for what you're working on. But as people start flocking towards the space, or as some of the players in the space get some renewed energy behind them to go do things, how fast and to what scale do you need to get to be commercially viable, given the context?
Yeah, again, great question. So I think we are going to be able to scale faster than most of our competitors, primarily because we are not building out new refining infrastructure. We're really the only approach that can provide a drop-in to existing hydrotreaters. EPCs already know how to build anaerobic digestion infrastructure. We're just adding on to that with new sensors and our technology. And then the ketonization step, as I pointed out, that's probably our biggest commercial scaling hurdle. So what we're seeing as a path is getting a pilot online next year. Our next step after that is doing a commercial demo. That first commercial demo is already that 1 million gallon tank that we prove out at that scale. And once we get to full scale, it's just copying and pasting that 1 million gallon tanks depending on how much feedstock is available.
Excellent. All right, Tim, we'll have to leave it there. Thank you for being here with us today.
Yeah, thanks so much.
And last but not least, David Stone, CEO of Carbogenesis, is going to join us here on stage. David gave me some grief last night for making him go last, but I told him that you leave the best for last, right? All right.
Hello, I'm David Song, founder and CEO of Carbogenesis. Carbogenesis' mission is to decarbonize through utilization with the goal of efficiently and rapidly converting CO2 into high-value, sustainable chemicals. At Carbogenesis, we have developed a groundbreaking integrated plasma catalysis two-stage process. It's highly scalable. We achieve precision tunability of the syngas composition. Our hardware is compact and modular. Finally, we are profitable even without subsidies. Plasma is special in that it breaks down inert molecules such as CO2 and water with equal efficacy. This allows any feed composition to be processed, ranging from super dry to stoichiometric dry to even electrified steam reforming. The output syngas composition is only determined by feed composition, as our process quantitatively converts all reactants to products. Indeed, as the graph on the upper right-hand corner shows, the experimental data coincide perfectly with the calculated curve. Why is compositional tunability important? Answer: syngas of tunable composition yields many important chemicals, such as carbon monoxide, methanol, SAF, and sustainable hydrogen. We can make all without relying on electrolysis of water to supplement hydrogen. I highlight the initial commercial targets for Carbogenesis and the attractive market size as well as CAGR of the individual segments on the right-hand column of this slide. As shown here, green methanol alone will far exceed the existing total market of gray methanol in 2 decades. Similarly, the glaring disparity between supply and demand of SAF, as well as the trajectory, implies that the world is desperately seeking a cost-parity solution to conventional jet fuel. Both products are multi-billion-dollar opportunities. Here's how our integrated two-stage process works. We use off-the-shelf and robust microwave components in the plasma reactor to break apart and recombine the activated species into syngas. The superhot effluent jet carries sufficient thermal energy to continue reaction automatically in the catalytic bed to completion. The photo on the right has the cover removed to show how collimated the plasma jet is. To make the process work, we have done over 50 iterations of fluid flow 3D simulation and actual metal cutting to confine the plasma and to direct the jet. This accumulated body of knowledge can't be easily replicated. Our fundamental business model is build, own, operate, i.e. BOO. To do so, we are building an extensive network of partners and customers. Specifically, Halliburton may play a pivotal manufacturing role as well as leverage its global reach to help expand our international customer base. Here is a schematic of a commercial scale skid housing 10 channels. This skid consumes 1 megawatt of microwave power. Through another innovation called amplification, an industrial scale plant would need only 25 to 50 such skids, which can easily deliver over 1,000 tons of methanol a day at over 30% IRR. Several notable advantages arise from this approach. Just like prefab houses, which are preferred over stick-built homes for their quality control, standardization, labor and cost savings, and speed of deployment, our skids could be fabricated by Halliburton, shipped to sites both domestically and internationally, stacked on location, and connected to utilities and feed gases. This slide shows the ecosystem and extensive partnership network already established or under discussion around Carbogenesis to ensure not only feed gas supply and customer offtake, but also manufacturing EPC support. Market forces driven by the motto of doing well while doing good will turbocharge the deployment of our innovative carbon utilization technology. Here is some background about me. I was formerly a tenured professor at the University of California, Berkeley. For the last 3 decades, I've been a serial entrepreneur. I owe the success of Carbogenesis to a talented and dedicated team of scientists and engineers. It's been a privilege to be working with them.
David, thank you so much for that presentation. For the economics to work, what is the diameter of the plasma you need, and where are you at now?
Thank you for the question. The diameter is on the order of 2 to 3 inches. Very compact. The height is 2 to 3 inches as well. Gas transits in this reactor in literally a few milliseconds. It could be 100% converted, but since we're using a 2-stage process, we intentionally flow the gas at such high velocity that there's a residual reaction to be completed in the catalyst bed because the plasma is super hot. It can be several thousand degrees Kelvin. It automatically heats the catalyst bed because the reaction is endothermic. We drive the completion automatically. I mentioned in my presentation there is also amplification. We can cheat by adding even more gas unreacted into the second stage, thus accruing even better economics. Just to give you an idea, the economics, we did a very elaborate technical economic analysis, a spreadsheet, a very conservatively levered IRR for our plant can be close to 50%, which is unheard of for CO2 utilization.
Yeah, this is very exciting. So you're already at scale for the size of the plasma.
We have a single channel. We're working with a couple of big companies. One is Tallgrass, who promises to give us 5 million tons of biogenic CO2 a year for us to convert into methanol. And we would like to work with Topsoe, UOP to make SAF. We produce the syngas, the downstream methanol loop, the downstream Fischer-Tropsch process. Other people have the technology. So it takes a village to build something, as you know.
You took 2 of my questions there. So syngas is your primary product. But I'm hearing you discuss this and seeing the presentation. There's other kind of higher end products coming off this. So what is your plan on diversifying maybe into those products and strategy for penetrating those markets?
Well, one possible strategy is to utilize the global reach that HalLabs has, 73 countries. You can launch our technology. You can fabricate the skids to Middle East, to Asia, over the world. We are a solution provider. We are collaborating with the EPC, very sophisticated EPC of the AI builders, the top 2 or 3 we're working with right now. I can't announce their names yet. I'm only allowed to say I'm working with Tallgrass at this moment. Hopefully working with HalLabs one day.
It's great to share the stage with a fellow Cal Bear.
Yes.
What is the purity required for the feedstock of the CO2 and the methane?
Yeah, thank you. Thank you. In fact, we're mixing the 2 gases. The hydrocarbon doesn't have to be just methane. Any crappy hydrocarbon flare gas, it can be a mixture of ethane, propane, etc. It can be naphtha. Hydrocarbon provides the hydrogen. And H2O is also mixed into the system. It's a ternary system to produce the right composition of syngas, perfect for making methanol and SAF. It takes 2-to-1 ratio. We can tinker with it. We can go all the way to hydrogen. You saw in the slide. We can go all the way to just CO, such called super dry reforming.
Very nicely done. Thank you. How do you control the system? And how do you ensure that you're not producing unreacted product or using excess energy and putting more energy in than you need to.
Yes. The control is actually a challenge that we overcame. It took, in my talk, over 50 fluid flow simulations, CAD simulations, really cutting the metal to make our reactor work smoothly. We can turn it on. It's like watching the paint dry. Plasma just go on until we have to go home. In fact, we've done the reaction because the temperature in the catalyst bed is much higher than SMR. It's 1,000 degrees instead of 850 degrees. The reaction even in the catalytic bed is very fast. No soot. Thus, we overcame the industrial handicap. That's why super dry reforming has never been practiced. I think we have a shot at making it practical because of the coupling of high temperature, partially reacted effluent. I call it amplification. We can cheat by adding more hydrocarbon in between the two stages, thus processing even more. That's the secret of amplification. So multiple things happen to make this work.
Help me understand a little bit about your microwave plasma source. If you take your first-of-a-kind plant, how many of these sources do you need?
Yes.
Or today it's very low kilowatts availability in the market because there is not a large market except semiconductors or maybe fertilizers. But would you be able to go with the existing sources or would you design much larger systems in order to be cost effective?
Okay, it's a great question. Civilian maximum power of magnetron is 100 kilowatt. That's a lot of power. The skid will have 10 channels, so 1 megawatt microwave power per skid. With amplification, we can provide auxiliary heating in the second stage that's processing 2-3 times more gas. So if you don't amplify, it's 30% IRR. If you amplify, 40 plus, 50 plus % IRR. It's I hesitate to disclose this because we would like our off-takers to take even methanol at gray methanol price, but we would like to get a little bit more premium because it's sustainable. Right? It's okay. Our plan is to roll out multiple single skid demonstration plants just to run it at various locations, and we have volunteers to do this. We even have volunteers to pay for the skids with us. But once demonstrated, it's just copy and paste. So manufacturer is, if we have our partner to do this, we don't have to have deep pocket.
Very good. David, thank you so much for coming and sharing with us today what you're working on. It's fantastic. And I want to first thank all of the 10 pitching companies. You guys are all doing the hard work. And, for me, success looks like agonizing over who we decide to ultimately bring in. And I can already tell that I'm going to agonize on this one. Thank you to everybody on the panel. Thank you to Maynard and Senator Hutchinson. Thank you to everybody that came here today. You got the full show. You got geopolitical drama, tearjerker, sci-fi. It's like better than going to the movies. So thank you. Thank you, everyone. And with that, we'll wrap up the whole week. Thanks.